and you look in the tail portion, and you find that that corresponds with a probability of 0.1587, or 15.87%. Same concept. We've been applying this for the past week. You guys understand this. Very similar, nuanced differences that are mostly terminology. That's it. But the actual concepts are very similar. So I want you to take a second and practice these. I'm not going to go over them. I'm just going to kind of show you what they are. So if you have a sample of n equals 4 scores, select it from a normal distribution with the mean of 40 and standard deviation of 16. What is the z-score for a sample mean of 42? So for a sample mean of 42, that tells us we have to use this formula right here. And so what we would essentially do is take 42 minus 40, divide it by the standard deviation of our population, divided by the square root of n. Because 42 is our sample mean, population mean is 40, standard error is equal to the standard deviation of the population divided by the square root of n. So you have to remember orders of operation with this. Okay, so remember 42 minus 40, you would put that in parentheses, and then the denominator would all be in parentheses together as well. Oops. And what do you get? It's not negative, but it's 0.25. So what is the probability of obtaining a sample mean? You have to remember these things when taking this test, because sometimes it'll say score, other times it's going to say mean. And if you hear or see sample mean, then you know you're working with standard error. That's the thing that's going to change. So of a sample mean larger than 42. Well, you have the z-score for 42, and so you could essentially draw it out, right? Put your little line there, shade that part, and you would go to your z-table, look for a z-score of 0.25, and then look for the column that gives information about the tail, because we are interested in the probability of obtaining a sample mean larger than 42. And the answer is 0.4013, or 40.13%. We've done this. You know how to do it. Slight changes in terminology, but the concepts are all the same. Okay. So, going back to a similar problem that we did as we did last week. So what is the range of values expected to capture the middle 80% of the distribution of sample means? And so what we're interested in is what is this sample mean and what is this sample mean? So we're going to apply the same logic that we did before whenever we were like, what is this score and what is this score? Well, we know that this is 80%, so if we divide it in half, this is 40% and this is 40%, 10 and 10. So what we can do is we can go to our z-table and we can look for the proportion of, we can look for the column where it gives information on the proportion or the probability of obtaining a score or a sample mean between the mean and the actual score or sample mean. So I think that that's column C. Let me check. Yeah, so the proportion between the mean and the z-score. That's going to be column D, actually. It's column D. And so you would go until you found 0.4. Okay, and so I'm going to do that right now. 0.4, 0.4. Okay, the closest I found was 0.3997, so I'll probably go with that one. And then I would scoot over to the z-score. The z-score that corresponds with a probability or proportion of 0.4 from the mean to the z-score to the actual score to the sample mean is 1.28. Oops. Okay. Sorry, I put these out of order. So you have here 1.28 and 1.28. So at that stage, let's see. Okay. So if we know that, so at this stage, what we're saying is, what is 1.28 z-scores above 500 if we know the sampling error of the distribution? Well, you can basically use this information to back calculate with this formula. You've done this before with individual scores. Instead of having an M here, you had an X. Instead of having standard error, you just had standard deviation. But you use the same logic to solve for it. And that is exactly what you would do here. And when you do that, you would find that the range of expected values for sample means would fall between 474.4 and 525.6. Values between that would capture 80% of the distribution. Okay, so more about standard error. So there will usually be a discrepancy between sample mean and the true population mean. This discrepancy is called the sampling error. This is a conceptual thing. The amount of sampling error varies across samples. When working with sample means, we use standard error. The variability of sampling error is measured by the standard error of the mean. And so, essentially what we're saying here is that sampling error is going to happen. There's going to be a discrepancy between the sample mean and the true population mean. It's going to vary across the different samples. But it's more of like a conceptual thing that we recognize and we understand, blah, 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 blah. But at the end of the day, how are we measuring that? How do we assess that? And how can we use some type of metric to help us understand the amount of error? And the way we do that is by standard error. Standard error is a way for us to measure and mathematically compute sampling error. It's an average, though. It's not particular to just one sample. So at the end of the day, the variability of sampling error is measured by standard error. So again, sampling error. It's a concept that a sample typically will not provide a perfectly accurate representation of a population. This is a why do they differ? Why does the sample differ from the population? This is what we talked about earlier in one of the first slides. Whenever we pull from a sample, it's not going to be, there's going to be people who are missed. Everybody has individual characteristics. Samples are unique. You're going to have variability. And so for all these reasons, there's going to be an element of sampling error. Standard error is a way to, it's supposed to say measure. Is a way to measure the average or standard distance between a sample mean and the population mean. So this is a how much do they differ. We know why they differ. Sampling error. How much do they differ? Standard error. Provides a method for measuring and defining sampling error. That's what it comes down to. So why do we care about standard error? Do we usually know the population mean? Usually not. But what are we trying to do? We are trying to use information gathered from a sample to infer information about a population. We're trying to describe a population from our samples. Sample means can be used to provide information about unknown population means, about unknown population parameters, but it's not perfect. We're going to have this element of sampling error. And so standard error tells us exactly how much imprecision there is. This gives us an idea about our sampling mean and is it really that reliable? If the sampling error or if the standard error is really, really large, is the sample mean probably a good approximation of the population mean? Probably not. And so standard error really gives us some insight into how well our sampling statistics, or our sample statistics represent the population. Okay, and so this just provides some more information about standard error and thinking about it in terms of population or sample size, things like that. So here, if you have a distribution for sampling means with an n of 1, so each sample only has an n of 1, we see that the standard error is equal to the standard deviation, and that's equal to 20. And so we can see here that there's a lot more variability than these compared to these right here. And that's kind of what this represents. As we increase in sample size, though, we see that the standard error is decreasing, and we also see that the variability in our distribution is getting smaller. And so by doing that, we are able to, this is a pictorial representation of how increasing sample size helps us to provide a more accurate, more precise estimate of the population whenever we only have a sample. And then when we increase our sample size to 100 and continue to resample, the standard error is quite small. And so you would expect with an n of 100 that the sample mean will be pretty representative, pretty near the mean of the population. Okay, so this just provides how standard error is represented in publications, things like that. Typically, you'll just do a bar. And so this is the mean of the sample, and then this is the standard error. So this is the mean of this sample, and this is the standard error. Same thing here. So it just provides us some information with how much variability there could potentially be around these means. Okay, so then bringing it all together and really thinking about what we're doing, why it matters, how we're going to apply it. So inferential statistics use sample data to draw general conclusions about the population. Oftentimes we don't know the specifics about the population. So sample information is not a perfectly accurate reflection of its population. There is that element of sampling error, and we use standard error to calculate the average distance from the population mean to our sample mean, and that's a way for us to quantify sampling mean on average. So the distance between sample and populations introduce uncertainty into inferential processes. And so this comes back to this idea that, it's not going to be a perfect science. We don't have a perfect science. We're working with individuals. They differ a lot. Can you fully generalize conclusions from one study to an entire population? Probably not. But we can do our best to try. and we can help move our science forward by doing these studies, trying to replicate them in different populations. And then if we're able to replicate them, that just provides more evidence for the robustness of these associations. So statistical techniques use probability to draw inferences from sample data. Going back to what we were talking about earlier. What is the probability of obtaining a sample mean of 525.6 or higher? What's the probability of obtaining a sample mean of higher than 525.6? 10%. That's what it comes down to.